Thank you so much, Craig. I truly appreciate it. Just give me one moment while I get the presentation up. All right. All right, so everybody should be able to see this. So my presentation today is on 3D printing tips, tricks, and hacks. The very first part of the presentation is going to be aimed towards kind of the technology itself behind 3D printing, what you really need to know before you purchase it, and then the second half of the presentation is going to be tips and tracks to help you with your 3D printing processes and hopefully streamline your workflow a little bit. So to begin with everything in designing in 3Shape, the very first thing that you need to know is you need to start with some sort of scanner or an impression of some sort, and then from there you're going to go into your design software, which would be like 3Shape, ExoCAD, Dental Wings, etc. From there, you will actually output a model or a structure that you can 3D print. So before you can even get close to 3D printing, you do need to have a CAD software, and before the CAD software, you will need a form of impression to be able to design a structure from it. So for 3D printing itself, actually, let's see, is this showing? Okay, there it is. So for 3D printing itself, the definition of 3D printing is a printing process that involves making a three-dimensional object from digital models by applying many thin layers of material on top of each other. So successive layers, one on top of another. So for those printing processes, there are multiple printing processes in the industry of 3D printing, but which one is correct for dental? So in the dental market, for FDM printers, you'll see the Balplast style printer, which is a very cool technology. It's an extrusion-based 3D printer. You'll also see SLS and SLM, that's selective laser sintering or selective laser melting, that we'll see for like RPD frameworks, bridge frameworks, full cast crowns. Really cool technology. And then also in dentistry, you'll see sterile lithography, which is the vat polymerization, which is the two on the top right. Underneath, there is other types of 3D printing, but the only one that you'll see would be like the polyjet, material jetting, which is on the bottom. This is very similar to like the Stratasys style printers. 3D Systems has some printers like this as well. But the other three that are across the bottom, you'll see in other industries outside of dentistry. So the main focus of 3D print technology that we're going to look at today is the process known as sterile lithography. Now, sterile lithography is the process of solidifying a photopolymer resin layer by layer that is activated by a UV light engine. So for this, there are a total of 3 different types of sterile lithography. When people think, or when you're doing your research stage, most of everybody will think that sterile lithography means that it's just using a laser, which is on the left-hand side. This is the very first form of sterile lithography, but it actually goes out into DLP, which would be the most popular, and then there's a newer form of sterile lithography, which is mask SLA. So let's see a little bit of a further breakdown. Now, all of these are sterile lithography, but there's 3 different types. So the least expensive type of sterile lithography that you'll see out there today, which is sterile lithography laser. This, as we can see, we have a UV laser as a light engine, and then we have a series of mirrors that directs the laser into the resin vat itself to cure the resin to the build plate. The 3 main competitors that I see in the dental industry right now would be Formlabs, DWS, and then XYZ has a 3D printer that prints with sterile lithography laser. Now, there is a downfall to this technology because it uses a laser. It takes a long time for it to actually print the object because it actually has to draw the full image for each layer that is being cured. So it's a very slow process. The most popular in the dental industry right now, which is considered DLP sterile lithography, is digital light processing. This is an extremely really cool technology that's the most popular in the industry right now. With that, we can see that it actually uses a DLP chip, which is invented from Texas Instruments. And how this process works, it actually has a DLP projector at the bottom, and it will actually project the whole slice all at once to cure, or the whole layer all at once, and it will repeat that process over and over again. So what would take the sterile lithography laser method maybe 10 seconds a layer or even longer, it's going to take a DLP projector to cure a whole layer in a matter of just 2 to 3 seconds, depending on the resin type. Now, the main game players that we see with this type of technology, obviously ASIGA, that's who Whitmix is a North America distributor for. Now, there are different competitors out there. So like Carbon uses DLP technology, NuPro 3D, EnvisionTech, Colzer, which is also a B9 Creations printer, Sprint Ray, Cudo 3D, 3D Systems, and Accurata. This is the most popular form of technology for dental 3D printing. This is going to be the fastest, and this is actually the most accurate to date. Now, there is a new form that has come out, which is very similar to DLP, but instead of it using a actual projector itself, it has a LED light, and then it has a LCD mask, which actually masks light out and allows the image to shine through. This is a really cool technology. It's really inexpensive. It's still in the process of becoming more reliable. The main players that we see in this would be Structo 3D, Frozen Make, Uniz, Anycubic, and Cudo 3D has a bean printer, which is, it's a very cool technology, but it hasn't been proven for accuracy that I've seen yet. But it's really cool technology. I think that we'll see probably in the future become better over time. Now, a lot of the questions that I get is like, you know, they'll purchase a 3D printer and they'll look and they'll watch it work, but they really don't understand how or what is actually going into it. So how does my 3D printer really work? So as we can see, we have on the right-hand side an animation that's happening, and it shows the separation process. And so the very first layer of any 3D printer for sterile lithography is going to have a burn-in layer. This is the most crucial layer, because if the burn-in layer does not stick to the build plate, then nothing there after that will. After the burn-in layer, we have what is called the normal layers. And so with that, it will be a reduced exposure time that's just needed to cure the actual layer itself, the layer thickness, and then a little bit of bleed through to allow it to adhere to the previous layer to that, which is known as cure through. After that, there are some speeds that need to be taken into consideration depending on how fragile the resin can be. So that'd be approach and separation speeds. There's a delays between the layers, after approach, after exposure, after separation. And then another part that goes into 3D printing for sterile lithography is XY scaling, which compensates for the amount of resin or how much the resin is shrinking. And then there's XY compensation, which compensates for growth. So all of these settings is going to depend on the actual material that you're using. So each material is going to have a different set of parameters. So something to keep in mind when you start getting into 3D printing, you know, when you're setting up your print job, you're going to want to choose the correct setting or the correct resin in your nesting software that you are using in your printer. You cannot choose a castable resin for your nesting software and then put model material in your printer and expect it to come out successfully. So just make sure whatever you're putting in the nesting software, you use the same material in the actual print vat itself, or resin vat. So as I mentioned earlier with the exposure times, there is a proper way of how to calculate exposure time. This is something that you don't see in the front unless you have a completely open source 3D printer. So like ASIGA is completely open source, we can use any photopolymer resin from any manufacturer and calibrate it to work in the printer itself. So each resin itself has a particular cure curve. And so the light engine is measured in a number called milliwatts per centimeter squared. So for that, the actual dosage of light needed to cure the proper layer is milliwatts, the strength of the light itself, times seconds. So that's how we can actually figure out the dosage of light. So if we go a little bit backwards in thinking, if I wanted to cure a 100, if you look at this table on the bottom part of the graph, the Y part, you're going to see 100. So this would be the amount of dosage needed. And so at 100, a dosage of light at 100, you'd be able to cure a total thickness a little bit greater than 150 microns. So with that, I would take the light intensity, let's say if it was 10 milliwatts per centimeter squared, I would divide that into the dosage of light of 100, which would give me 10 seconds. So for this exact resin, if I wanted to cure 150 microns, I would need 10 seconds of exposure with that current light. This is a little more technical. I'd be more than happy to go over this at a later date or at a later time if needed with anybody. So when you're purchasing a printer, one of the most confusing parts is defining how accurate is the printer itself. So for sterile lithography laser, this is the XY accuracy is going to be as accurate as the laser itself. So the most popular 3D printer for sterile lithography laser has a minimum feature spot size of 140 microns. So the smallest feature you'll be able to print is 140 microns. Now DLP, which uses pixels, so if you're looking at your computer screen, that is actually made up of thousands of pixels. It's similar technology for the DLP projector. And so that can have a minimum pixel size of, I've seen, down to even 25 microns. Extremely small, which would make it extremely accurate. And then mask SLA is very similar. It has a pixel size as well, which I've seen around, it's been roughly around the 175 or 100 micron XY pixel size. So to actually see this, we'll see this here in a moment, how accuracy can make a difference in how the object is formed. So with XY resolution, we can see, this is what would be defined previously with that pixel size or spot laser size. I can see that I have two different accuracies here on the screen. On the left side, this was a 30 micron pixel, and then on the right hand side was a 100 micron pixel XY resolution. So we can see the object on the left is going to have a higher quality, a more accurate circle being printed versus the object on the right. So when we're looking at 3D printers, if they state that you have, or if there's a 3D printer that states they have a XY resolution of 25 microns, that's going to be extremely accurate, versus let's say if they have a printer that says I have an XY resolution of 140 microns, it is not going to be as comparable for precision. It will never be able to get the proper amount of detail. Something else that is confused is Z resolution. I see this on a daily basis. I look at 3D printers every day from other manufacturers, and I always like to see what their resolution is defined as. And a lot of competitors will only show the Z resolution. Well, Z resolution really doesn't define the accuracy for, like, it's not going to be true usable accuracy. This is going to more or less give you a higher quality surface finish. So we can see between the two structures, the structure on the left has a more stair-stepped like feature versus the object on the right. Now there's a trade-off. If you go into a higher Z resolution or printing in thinner micron layers like 50 microns versus 100 microns being on the left, the object on the right is going to take twice as long to print versus the object on the left. So this is something that you'll have to go through on the end users, figuring out what layer thickness you want to print a structure in. But whenever you're looking at 3D printers and they're defining the accuracy, make sure that you look at the XY precision first. If that is not below 100 microns, I would not even entertain it as a dental 3D printer. For Z resolution, you'll want to see really, anything. If you can get down to 25 microns or 10 microns, that's great. But realistically, mostly everything that all of our laboratories print is going to be at a 50 micron resolution up to 100, depending on the object itself. So to take XY accuracy even one step greater, there is a feature called anti-aliasing. I've only seen this on the most higher quality 3D printers. Anti-aliasing is a technique used to add greater realism to a digital image by smoothing jagged edges on curved lines and diagonals. So we can see this is a circle that was projected with anti-aliasing turned on. And what it does is actually just smooths out where that stair-step external edges are. So if you look at, if anybody has ever received a model from our print services here at Whitmix, and they received a dental model from the Asiga 3D printer, the first thing that most people notice is that the surface quality of it is so smooth. This is how the Asiga printer is able to achieve that. So if you're looking at 3D printers, make sure that you can have this feature of anti-aliasing. It's super cool. So besides actually stating on paper what a printer can actually achieve, we need to be able to show the actual precision at hand. So how can we prove the precision of a printed object? One way of doing that is actually overlaying a scan of, for example, we have 3 sets of models here. They're all the same STL file printed on 3 different printers. What we did is we actually would print the model, and then we would scan the model afterwards and then overlay it or compare it to the scan model to the actual STL file of the model that was printed. With that, we can see where we have any sort of accuracy loss. So the printer, or the scan on the left, is actually from an Asiga 3D printer, a Pro 275. I can see that it's actually extremely accurate, between 75 and 75 plus or minus microns. We had a 92.3% match. And so since it's printed on a Pro 275, the XY accuracy is 75 microns. That's why we're going to choose plus or minus 75 for the deviation. Actually, all 3 of these printers had a accuracy of 75 microns in the XY. And I can see the printer on the left, which is Asiga, had a 92.3% direct match from the printed object to the actual STL file, extremely accurate. The printer in the middle is actually the other 2 printers on the right. They are over $100,000 to own. The one in the middle only had about an 80% match. I can see, if we're looking at it in the occlusal grooves, we can see that it lost its resolution in the z-axis. This may have been printed at a higher micron level. It was still fairly accurate though in the XY plane. And then the printer on the right had an 88.7 match. This was once again over $100,000 for this printer as well. And you can see that it lost a little bit in its Z resolution. But the X and Y looked very accurate. So this is great because we used a software called 3D Reshaper for this comparison. 3D Systems has a comparison software as well, but a lot of laboratories, they're not going to spend the money just to be able to compare their models. So how can you compare this on your end? Well, it's very easy. If you have 3Shape or even exocad or dental wings, there's a process of doing this. So what I would do if I was using 3Shape, if I wanted to compare my models that I'm printing to the digital model to see if I'm actually losing any sort of precision or that my models are actually accurate, if I'm questioning them, I'm going to simply create an order form for a coping, and I'm going to place a pre-preparation scan as well. From here, when I open up the scan software, I will scan my the model that I printed, and then for the pre-preparation scan setting, I can actually import the scan. So if you see on the bottom left of the order form, this is 3Shapes. I can import a STL file or a DCM. So I'm going to import in my STL file of the model that I sent to the printer, and I'm going to overlay the 2. So from here, after I align those 2, I can do a 2D cross-section and actually see where I'm deviating. This is a great way that you can do a quality in-house check on your 3D printer to make sure it's printing the way it's supposed to. So I can see with this model, I had a difference of 65 microns on my interproximal contacts, which is pretty large. So if I was to actually do a buildup on this, a porcelain buildup, I would have actually made my contacts way too heavy, and then when the doctor would have received my final restoration, he would have been a little irritated that he had to adjust so much on it. So for that, you'd have to go back to the drawing board, figure out, is it my printer, or is it the resin that I'm using, or just contact tech support and they'll be able to help you out depending on who you purchase the printer from. But this is a great way that you can check and validate that your 3D printer is printing accurately without having to purchase an external software to do a comparison. So from here, we covered the 3D printers, but what you need to know about 3D print resins, all of this information is extremely important. A lot of printers that you'll see out there, they're going to come in multiple wavelengths, so 385 and 405 nanometers wavelengths. We sell, at Wimix, we only sell the 385 nanometer light source 3D printers. Reason why? It's a lot easier to work with. Some of the bonuses is that the light penetration is controllable versus 405 is not as controllable. It's just all around better print quality for printing clear resins. You can actually print a true clear resin with 385 versus 405. They're going to have tints in it to actually allow the light from not penetrating all the way through. Now, when you are choosing your printers, if you choose a 385 nanometer printer, you're going to have the best results with purchasing a resin that was manufactured around the 385 spectrum. The same way for the 405 resin, you're going to want to purchase, if you purchase a printer with a 405 light source on it, you need to use a resin that is manufactured for that 405 nanometer light source. Now, I have used 405 nanometer resin in a 385 nanometer printer, and I've had great success. But I have also used a 385 resin in a 405 printer, and that you will have issues of the resin actually, or light actually curing resin in areas that you don't want. So it is a little bit of cross-compatible. If you have a 385 printer, you can print both 385 and 405 resins, but 405 printer, you're stuck with the 405 resin. So there are health hazards that come with handling resin. So if you get it on your skin, you can actually receive rashes and have allergic reactions and dermatitis. So please wear gloves at all times when handling the resin itself. I know when I first started, I'm guilty. I'd take a print, take it directly off the build plate and grab it with my hands, put it in the alcohol, not realizing that I was exposing myself to multiple chemicals that can be extremely harmful. Eye contact, if you put it in your eyes, just don't use it as eye drops. Realistically, it can cause issues with excessive tearing, itchiness, even damage to your eyes. Inhalation as well. Some resins, they actually put off a lot of fumes during the curing process, and even in the liquid state, if you actually smell the different resins, some of them smell really bad. You don't want to huff that in or breathe that in. So depending on the resins, you will want to wear a face mask or a respirator, depending on how toxic it is. And of course, if you ingest any, you can actually become sick to your stomach or even vomit. So please do not use this as hand lotion. Any of the resins, do not use it as eye drops. Do not breathe it in and do not drink it. It seems pretty common sense, but you're going to get it on your skin, or you could potentially get it on your eyes. So whenever you're handling resin itself, I highly recommend wearing gloves and even protective glasses if possible. Now, how to handle it? Wear an apron or a lab coat. It will stain your clothes, so if you accidentally get resin on your clothes, you will forever damage it. A great example of this is one of our technicians was moving a resin tray with clear resin inside of it. It looked like it was an empty, brand new resin tray, and he lifted it up and tilted it back. It actually splashed all down his shirt, and it is forever starched. It's extremely stiff now, and you can't get the stain out. So please, wear some sort of protective clothing, or wear clothing that you don't care if you get resin on it. Vinyl nitrate gloves, safety glasses, a mask depending on how strong the fumes are from it. Now the ideal print environment is going to be clean, well ventilated. I cannot stress clean enough. Really, if you can put it in a dust-free environment, which is almost impossible in a laboratory, that'd be ideal. Or if you can keep it away from, as far away from the model room, that'd be ideal. Then if you can, emergency eye wash station. I know some of the larger laboratories do have that. We have it here at Widmix, obviously. And so if you ever get in your eyes, you can immediately go flush your eyes. So here's some tips for working with resin. So when you're using it, it's extremely important to read the instructions of use, because that's going to tell you exactly how long it needs to be mixed for. It'll tell you the daily maintenance of the resin that needs to be handled before printing itself. So please read the instructions of use. Some resins need to be heated up before using. Some of them do not. Some need to be mixed for 2.5 or 3 hours. Some need to be mixed for 5 minutes. So definitely read the instructions of use to get the best results from your resin itself. Now, if you ever have any failed prints, a great way to clean your resin to remove debris is to use a paint strainer. I recommend a 200 micron mesh or smaller. The smaller you go, though, the longer it takes for your resin to strain. But 200 microns or 0.2 millimeters should be a fine enough mesh to be able to strain your resin. From there, storing your resin bottles, I highly recommend storing them in a cabinet. If your resin bottle has a lighter color cap, light can actually bleed through that and actually solidify the cap onto the bottle, and it's almost impossible to remove. You have to get a couple wrenches out. So please keep those for best results. Keep your resin bottle stored in like a cabinet. And then from there, resin trays, if you're not using them, almost all the resin trays are going to come in a cardboard box. Go ahead and place that resin tray when you're not using it. Place it into a cardboard box, and then place that cardboard box into a cabinet to prevent light from exposing to it. It is a photopolymer resin, so if light gets to it, it can start to react the resin to cure itself. So what do you want to look for when purchasing resin itself? If you have a open source 3D printer where you can use resin from other manufacturers, there's different areas that you want to look at when choosing the resin itself. So immediately right off the bat, you want to look for accuracy. And so a low shrinkage and low warpage are two things you want to look for immediately when choosing a resin itself. The higher end brands like Widmix or Detax, Procedure, Nextent, they are going to have lower shrinkage values to them. If you go to like Fun to Do resins or Maker Juice, they have a resin that they manufacture. Those ones are going to have higher shrinkage and extremely high warpage contents. So they'd be fine for creating like prototypes or toys, but not great for dentistry. A third segment you want to look at is make sure that the pigment stays suspended. So resin itself is very similar to how paint is. They have pigments and blockers and photo initiators inside the resin itself, and over time they'll actually settle out in the resin tray or the resin bottle. So you definitely want to mix it up before using, but if you have a resin that has that can suspend pigments for a longer period of time, you will spend less time storing your resin and more time printing, which is what you want to look for. Viscosity plays a role. So if you have a resin that is very thin, like water, you're going to have it splashing all over the place when you're printing. Or if it's thick like honey, you can have issues of it taking a long time to print. So there is an ideal viscosity, and if you have questions about that, I'd be more than happy to answer that later. Easy post-processing. You don't want to purchase something that's going to take forever to be able to clean after printing. You want to definitely look at the post-processing of a particular resin before purchasing it. It may require a special curing unit. It may require a special cleaning liquid. Maybe the liquid that you have to clean it with is more expensive than the resin itself. So definitely look at the post-processing part before purchasing a resin. Low odor is ideal. And then biocompatibility. When you're looking at a resin, if it has to meet some sort of specific biocompatibility, you're going to want to look at definitely how to post-process it, how to clean it. What is it rated for? Is it a class 1 or a class 2 medical device? Is it actually a class 2 in the United States medical device, or is it a class 2A, which is only for Europe? You know, you need to look at those parts before using it. And then you get what you pay for. Higher quality resins, you spend more money for it, but you get better results from the higher quality resins versus the $30, $40, $50 bottle of resin. You know, you may have poor results with those. So how to post-process printed parts. So I cannot stress this enough. For the best results, follow the instructions of use provided by the resin manufacturer. Now, this is mandatory for biocompatible resins. If you're not using a biocompatible, or if you're using a biocompatible resin, you have to follow that instructions of use of how to clean it and how to post-cure it to a T, or else you are not biocompatible. So how to clean? Most resins, they're going to have, you're going to use an isopropyl alcohol bath, 90% or greater. If you go to a medical supply store, they should have 99%. I recommend, and most resin manufacturers are going to recommend, a 2-wash system of some sort. I recommend an ultrasonic cleaner. We'll do a dirty bath for 5 minutes and a clean bath for 5 minutes. So you'll do a 2-wash system. If the printed objects are shiny or a little bit slimy in texture, that means that they still have active resin on it. You need to go back to the alcohol baths in the ultrasonic cleaner or in your cleaning device for a couple more minutes to help break down that resin that's still resting on the model. Now, how to cure? You want to make sure that the objects are completely dry and, of course, free from any resin. Most resins, they're going to have a light cycle between 5 to 10 minutes. It really, your post-curing is for the final surface cure of the object. It's not going to do an extremely deep cure. It's going to be the first couple millimeters on the external surface of a printed object. Now, if you're the acceptable curing unit you want to use for your resin, you want to do the research. If it's a biocompatible resin, it may need a curing unit that requires heat and light together, or a oxygen inhibition layer and light together, versus if it's a non-biocompatible resin, well, you can use just about really any curing unit that fits in the light spectrum that the instructions of use require. So you definitely want to do your research. Now, I do have a video of how to remove objects from the build plate. There are some ideal tools for this that I recommend, which is a number 2 X-Acto knife handle. Make sure it's the number 2. It's the wider handle. The number 1 is too small. And then the 1/2-inch wide X-Acto chisel blade and a jeweler's hammer. So I actually have a video here of Whitmix's own Brandon Smith. Let me go ahead and pull this video up. Now, it may be a little hard to hear. If you have any issues with hearing it, we will send this link to this video afterwards, and I'll try to also commentate for it.
All right, this is Brandon Smith with Whitmix, post-processing models off of the Max printer. The post-processing is the same for the Max as well as the Pro 275.
So what he's going to do is going to place the models itself to the side.
Using an X-Acto knife
chisel blade and a gold-tipped hammer to remove these models.
And you're simply just going to place the chisel blade right to the base of the model and just slowly tap. And you can see just with that tapping, the blade actually itself will get underneath the edge of the model, and then the model will just pop right off.
For 5 minutes in the ultrasonic, and then we'll put them in a clean bath for an additional 5 minutes in the ultrasonic. Once they come out of here, they'll go into a light cure box, and they'll go in there for an additional 5 minutes. And then that finishes out the post-processing. Just make sure that before you put them in the light cure box that you have completely dried the models, no resin or alcohol residue left on them. That way when they come out, they're not tacky. To clean your build head, just use a regular paper towel and some of the alcohol that you use for post-processing, which it's just regular IPA alcohol. You can get it at any drugstore. Squirt a little on your build head and just wipe it down. Make sure that when you do this, you always wear gloves. This resin can be toxic before it's cured, so you don't want to expose your skin to it. And just once you clean your build head, it goes back in and you're ready for your next print job.
And total post-processing, 15 to 20 minutes?
Yeah, about 15 to 20 minutes.
Thanks, Brandon.
You're welcome.
So we'll send that video to everyone. As you can see, it's extremely easy to remove the objects using these tools. From there, you'll take the models out, put it in the first bath of alcohol, which is considered the dirty bath. Run that for 5 minutes or so, depending on the instructions of use. And then from there, you'll take the objects out and then place them into the, we'll place those into the clean bath for another 5 minutes, bring them out, let them air dry, or blow them off with compressed air, and then from there, you will place it into the UV curing unit that is required for that resin. All right, so from here, it says how to dispose, or we need to cover how to dispose unwanted resin waste. So if it's unpolymerized resin, so uncured resin is hazardous to the environment. If you need to dispose uncured resin or contaminated resin that you cannot cure, you'll need to check with local government on how to do this. So this is regulated at the city level. But if it's there's a tip for dirty alcohol as well for exposing or disposing that. So you can actually take all of your dirty alcohol from all these models that you've cured and place it into like a 5-gallon bucket and just keep storing it up. From there, place that bucket actually outside. The alcohol will evaporate, and then the sun will actually polymerize the active resin. So you'll have like a chunk of cured resin in the bottom of the 5-gallon bucket. So that's an easy way to kind of dispose of your alcohol and of the active resin. For polymerized waste, you can simply just throw in the trash. The final reaction has occurred, so there's no any toxic parts of the actual models or structures themselves, so you can just simply throw them away. You can actually cure unwanted resin. So let's say if you had liquid resin you no longer wanted, you can put it like in a clear cup or even a Ziploc bag, pour some in, throw that into your curing unit that you have, solidify it, and then from there you can throw that away properly without having any active resin. So that's a little trick. And then we get this question a lot: is can we recycle cured resin? The answer is no. Not this time. There isn't a proper way to break down the materials to properly recycle them for further use. All right. All right, so I have some 3D printing design and support tips for you guys. So for the most popular thing that 3D printers are being used for is currently models. Obviously from intraoral scans, or if you're scanning impressions, you need a way for most cases, you're going to want to have a model to check to. So these settings are going to be set for 3Shape for the model. And these are settings to live by for 3Shape if you want to print a hollow model. Solid models, there are no tricks for it. It's just a solid model. But for hollow, you want to at least have it be at least 2 millimeters thick. In 3Shape in the control panel, there's a setting called variable thickness. You want to turn that on. If we look at the structure on the right, the photo, that 2D cross section, if we see how the internal surface is shaped like a V, that is because we have that variable thickness on. And then another structure or another setting you want turned on is you want the side drain holes turned on. In 3Shape, they're set 3x3 circle, and they default at 10 millimeters apart. Don't go any greater than 15. What this does is this actually allows the resin to breathe throughout the printing process. So if this was a solid model or a hollow model, but the sides are all solid, well, when I go to print it, when it goes to close that hollow structure, it's actually going to trap resin. It's going to create like a force, a vacuum. And when it goes to close off that model, when it pushes down, you can actually have it deform the layers. So it's extremely important to actually place those holes on the side of a hollow model to allow resin to breathe in and out during the printing process. So I do have some screen captures of some improper designs. So this is a hollow model. It has the variable thickness turned on the object on the left, but we can see it doesn't have the side drain holes. So would I be able to print this? Yes, but the surface quality on it is going to be extremely poor. And then the model on the right is a hollow model, but if we look at it, they actually closed off the bottom or the base of it, and so it had trapped liquid resin on the inside. This is actually a customer of ours. They called up and said, hey, you know, our models are leaking liquid, and we're like, there's no way because they're printing solid. Well, we did a 2D cross section of it and realized that it was actually hollowed out on the internal surface of it, and it had a solid base and solid sides. That is something you don't want to do because it's going to have that liquid resin on the inside. You're not going to be saving any sort of money for that. Now for die design, there's for 3Shape the most printer friendly design. If we can see on the photo on the left, see how the base of the die moves up and then it tapers up slowly to the actual size of the die, versus the object on the right, it creates a 90-degree structure from the pin to the actual surface of the die. We want it to have that taper like on the left-hand side. So these settings are all found in 3Shape. The pin type, you can do die-shaped pin is what we prefer. The die shape, you can either do standard or free. Standard is going to be square. Free is going to follow the shape of the margin line. The base height needs to be at least 5 millimeters. The pin height needs to be, I recommend, at least 2 millimeters. And then the settings to actually get that taper along the edge from where it goes from the pin to the actual die. Those two, it's a combination of two settings. You want to have a base stop surface width of 0.1 millimeters and then a base stop surface angle of 40 degrees. So if you actually put that in, you'll be able to actually have that tapered edge for your die. This design allows us to print this die without having to place supports under the corners. With the die on the right, I would actually have to place a support under each corner, which is going to cause, it's going to prevent the model from actually fitting properly. Also, with the printing process, if you're using a improper exposure time, or if your printer itself doesn't have the proper exposure time to the layers, you can actually have resting resin cure under this die, which would prevent it from seating into the die hole properly or all the way down. So speaking of removable dies, there's a formula to actually achieve this. Whenever somebody purchases a printer, they'll go ahead and they'll actually use the standard setting for Model Builder, whether it's ExoCAD, 3Shape, or Dental Wings. And if that die does not fit that socket, the printer is inaccurate. Well, that can be true if you have a very low quality printer, but if you're using one of the higher end printers, you know, it's not so much the printer that's going to be inaccurate, it's going to be that your settings are not appropriate for the material or the printer technology. So the removable die formula, this is if you're using a DLP 3D printer or a mask SLA 3D printer. This does not really work that well for the laser based sterile lithography, which would be like the Formlabs printer, but this is going to work great if you're using a DLP or mask SLA. So it's all in the pixels. So what you'd want is, there's a formula to follow, is the die to model spacing, which is on the left, plus the friction bar overlap, which is how far the overlap is lapping into the die, needs to equal 2 pixels, at least 2 pixels in width. So the pixel width is defined by the XY accuracy of the printer. So for example, on our Sega Pro 275, it has a 75 micron pixel. So with our Whitmix Varimodel OS removable die settings, we have a die to model spacing of 100 microns. So from the wall of that removable die socket to the actual die is 100 microns. And then the amount that the friction bar overlaps the die is 50 microns. And if I add that up, it equals 2 pixels in width, which is 150 microns. The reason why this is extremely important, if this number was less than, let's say, a single pixel, the slicing software will not be able to slice and project the actual friction bars. And if it can't project the friction bars, then your die is either going to be extremely loose or your die is going to be extremely tight. So you need to be able to design your removable die settings so that it actually, your printer itself will actually project or show the friction bars in the slicing software. If anybody's struggling with removable dies, please give me a call. I'll be more than happy to run through it, or give any of the techs here at Whitmix a call. We'll be able to help you through that. But the formula to live by is die to model spacing plus friction bar overlap is going to equal 2 pixels, or the XY accuracy of a printer times 2. Also, for analogs, so if you're doing like an implant model and you have the analog that's to slide in the bottom of the model to screw your implant to, a great starting point for that, I would use 50 microns for that setting. So that'd be analog to model spacing, which is place that at 50.05 millimeters or 50 microns. And then from there, print your model. It may be a little loose, it may be a little tight. From there, you can adjust to get it perfect. Now, castable resin design and support tips. So for the wall thickness of a castable, this is all going to depend, of course, on the resin itself, but I would go no less than 0.3 millimeters, or what is described in the instructions of use. Margin line offset should be no less than the XY accuracy of the printer being used. So the margin line offset of your castable design, if it's for a crown and bridge, should be no less than 1 pixel width. If it's less than a pixel, the printer itself will not be able to achieve that margin line, and you may potentially even have a short margin at that point. Cement gaps, you should not change if the resin is scaled properly in the printer's CAM settings. So the cement gap should remain the same of what you're already using. If you're doing an RPD for the clasp and arms, you're going to want to start at 1 millimeter and then work your way down. Once again, this is going to be dependent on the actual castable resin and how strong it is. And then for placing supports, you're going to want to put that on the non-prep surface or on the occlusal surface of your design. You obviously don't want to put it on the internal surface of a crown, because then it won't actually fit on the die. Surgical guides and splint design tips. So for surgical guides, I would make no less than 2 millimeters. The teeth to tissue, or teeth / tissue to guide offset needs to be, I'd recommend starting at 100 microns and then go from there. Once again, it's going to depend on the resin. The sleeve to guide offset would be 50 microns. That's a great starting point. And then, of course, when you're designing your surgical guides, include visual aids. Place windows in the actual surgical guide, so when the dentist is using the surgical guide, when he places it into the patient's mouth, he has a way to visually check to make sure the surgical guide is properly seated in the patient's mouth. Splints, the wall thickness, you don't want to go any less than 1 millimeter. Occlusal thickness, no less than 2. The teeth to tissue offset is going to be similar to surgical guides, 100 microns. And of course, when you're designing your splint in the Splint software, remember to block out undercuts during the design process. For 3D printing, all of the materials that are available or will become available for splints is currently going to be a hard splint. It won't be a soft splint, so you will have to block out the undercuts for it to seat properly. Now, I see this a lot. The support angle for how we're going to actually support a structure, horizontal versus 45-degree versus vertical. The most accurate, hands down, way to print a structure is going to be to print it horizontal to the build plate. This is you're actually being able to achieve the XY precision of your 3D printer. The prints are also going to be a lot faster, but it can be challenging to support objects with a larger surface area. So most print softwares, you're going to have the ability to optimize your support structures, and really your provider of the resin or the 3D printer should already have that covered beforehand. But if you're printing like a large model on supports, if you have delamination from that, there's a way that you can increase the support size to have a greater adhesion to the supported object. All crown and bridge applications should be printed horizontal to the build plate if possible. Now, if we move on to a 45-degree, you will lose a little bit of precision, not much, it's very minimal. The print times are going to increase because of the height of the structure is increased. This is the most printer-friendly orientation, and the reason why is the surface area of the object that is being printed is very small. And so when the printer goes to separate between layers, there's a minimal force that's pulling against it. Surgical guides, splints, RPD frameworks, denture bases can all be printed this way. It's still going to be extremely precise. Even some crown and bridge you could print at a 45, but if it's a crown and bridge model or an implant model, I would not print out a 45. I'd always print that horizontal to the build plate. And then the last position to print an object, if we're to print it vertical, this is where you can actually lose the most detail with printing a structure. It's going to have the longest print times. It may lead to supports in areas that are not desirable, let's say like on the occlusal surface of a model. Now there's an upside, it frees up the build space for more objects. Now this vertical printing is great for and acceptable for like orthodontic models or appliances, ortho appliances, or like a hot topic right now is obviously creating clear aligners. So if you were to create your clear aligner models or your aligner models in 3Shape or whatever design software you wanted, from there you could be able to place them all vertically on the build plate, fit all of them on for that patient, and they would be accurate enough to be able to create your vacuum formed appliance. So let's cover real quick the types of print failures and how to overcome them. So poor adhesion to the build plate is the most frustrating failure that you'll have, because you just waited 3 to 1 hours or 1 hour for the objects to print, and the build head comes up, you're super excited, and then there's nothing there, or there's delamination that we can see in the photos. So how can we overcome that? The causes is the first number one cause that I see is improper calibration of the build head. The build head is not truly parallel to the image plane below it, or it's maybe calibrated too far away from the image plane, so it can't actually have the correct exposure time for the burn-in layer. Or you could have selected the wrong material in the print settings, and so let's say we selected cast, but then we put model material in the printer. Well, it's going to have incorrect exposure times. Dirty optics, if the glass that the resin sits on is dirty, or if the mirrors are dirty, that can cause failed prints. Or last but not least, let's say the resin has a very high warpage characteristic, it can actually delaminate itself from the build plate. So resolutions, how we can solve this issue would be calibrate the build head to be parallel to the projection plane, increase the burn-in exposure time. This is only possible if you have a open source 3D printer where you can actually tweak those settings if needed. You can create mechanical retention to the build plate surface by taking like some sandpaper and actually sanding it down. Now, if your build plate has a special coating on it, do not sand down that coating. So you want to check with the manufacturer before you do that. And then, of course, clean your printer. The next form of failures that we see is delamination. So this is when you're printing along and all of a sudden half the model starts to split off. So this is caused by improper, number one thing would be improper normal layering exposure times. This happens if you have a fluctuation in UV light source intensity. So we see this a lot with some of the lower end 3D printers where their UV light source is just up and down. It doesn't actually have a high quality LED in it. And let's say if that light source drops halfway through the print, you can have delamination like that. Dirty optics causes that. A worn resin tray, let's say your resin vat or resin tray is towards the end of its life cycle, that can cause that type of failure. Or if the objects itself was not supported properly, let's say it didn't have proper internal supports, you can receive a delamination like that. And so resolutions for this would be, first, you need to verify that you have the correct material selected for printing. Clean the printer, replace the resin tray, and then apply manual supports if the automatic support generation is not enough. And then I can see in this photo, excessive flashing around the objects. So if you look at the photo, it's kind of hard to see, but you can see some like little growth, the stringy growths. So what can be caused from this is overexposure during the print cycles, or the printer is dirty, the optics are cloudy, light is scattering and it's actually curing resin outside of the desirable areas. Or let's say if you left your resin tray open or the printer open and it actually cured resting resin, it can create a film on the top, which would actually create these flash-like structures. If you had a previously failed print and you did not clean it, then that can cause that. So the best way to overcome this type of flash is if you see it, immediately go ahead and strain your resin. Use a paint strainer, 200 microns like we covered earlier. Strain the resin, get all the flash out of it, and then go ahead, pour that resin that was strained back into the resin tray, and then try printing again and see if you have the same issues. Another failure we see is improper support generation. So on this photo, I can see where on the left-hand side of the model, I can see where the supports actually started to peel away. So tips to reduce it: clean it. I probably sound a little bit like a broken record, but really, you need to keep your printer clean, especially anything that deals with the optics or light shining through. It needs to be cleaned on a regular basis, even daily, depending on how often you use the printer. Use the auto support function, and if you're having some sort of failure with that, increase the support contact width if you can. So I get this question a lot. Can we save a failed print? The answer is no. Once a print has failed, you have to start over. You'll have to clean out the resin vat, whether if you're curing a rectangle and pulling out all the objects that are stuck to the resin vat itself, and you will have to clean off the build head before you start your next print. So you'd have to start fresh, unfortunately. Unlike milling, if you failed or if you had an improper mill, if you leave the puck inside the mill, you can actually re-mill on top of it and hopefully recover the object that you were milling. 3D printing is completely opposite. You cannot. So for some 3D printing fun, there's a lot of free softwares out there that you can use. So, most importantly, besides using 3D printer for work, there is a way that you can have fun with it on the side as well. So some free softwares would be like Autodesk Fusion 360 is a free CAD software, Mesh Mixer. And then if you already want to receive STL files that you want to print, Thingiverse.com, super cool website. You can download just about anything you could ever want in STL format and place it on your 3D printer, from remote control cars to toys to whistles, really anything. Super cool website. I highly recommend checking it out. Don't let the boss know, because they may not like it. But if you purchase a inexpensive resin, a hobbyist resin, then you'll be able to print a lot of these structures and have a lot of fun with it. So some key takeaways: do your homework before purchasing a printer, receive test prints and compare them. Find out if you have any sort of material restrictions for the printer that you're purchasing. I highly recommend looking at the open source 3D printers or going that route so you can use any resin from any manufacturer. Read the instructions of use for everything, for the printer, for the resin, for everything. Design with 3D printing in mind. Keep your printer clean and take time to understand the technology and have fun. So this is the conclusion of my presentation. If you guys have any questions, please feel free to ask. I'd be more than happy to answer all of them if we have time.
Okay, Cory, there are a couple of questions.
Okay.
First one, how do you find the die to model spacing?
Die to model spacing. So, like, how do you find the setting? The settings in the control panel itself. So if you're using 3Shape, if you open up the control panel, there's a I can't remember the exact wording. I think it's like model settings. It's over on the right hand side. You'll select that, and then you'll find die to model spacing and friction bar overlap. There's a header at the top with a column. You'll choose the material that you're wanting to print with, and then you can modify that setting there.
Okay, great. That was the second question, was the friction bar overlap, and you just answered that. So
cool.
Okay, it looks like those are the only two that popped up now. I'm sure there'll be more later. And for those of you who would like to reach out, you will be emailed if you signed up for this course with the instructions on how to get CE credits for it. There will be a test that you can take, a short one, just 10 questions. You'll be able to do that on SurveyMonkey, and we'll give you those instructions along with that email tomorrow. We thank you for joining us today. We will have more upcoming webinars. In fact, the next one will be with Al Flastry on coloring zirconia. So any that you're interested in, please check out our website again, www.whitmix.com. Go to the top of the page at webinars, and you'll be able to see the list of things that are out there and available for you currently, and those things that are upcoming. Thanks again for joining us. We'll see you later.